we are going to continue this one. Yeah. So the search agent part 2. Yeah. Okay. So part 1 already given in the previous lecture about the very important part. Yeah. BFS. Yeah. Yeah. Breadth first search and also depth first search. Yeah, DFS. So now we continue with this topic about the depth limited search, ALS, and also iterative deepening search, IDS, and bidirectional search or BDS, and also uniform cost search or UCS. So before we continue this part, please you read the chapter 3, because I have something to do for 15 minutes or 20 minutes, and after that I will come back as usual, and then we will continue. But before we proceed with this topic, we have some additional content about what's that, the BFS and DFS, to clarify. And then after that we continue with this part. So I'm going to show you the textbook that you need to read first, before we proceed. The third edition, Artificial Intelligence Modern Approach. All right, so stop this one and change with this textbook, and you have around 20 minutes to learn to read these materials. I think you have downloaded this part, because this book is very important. Almost of all the content of this module are taken from this textbook. All right. So this one. So AI, introduction, intelligent agent. So problem solving. This is the this one. Chapter 3 about the second part. The first part is AI, introduction. Second part, problem solving, and you read this one. The third chapter. Chapter 3, solving problems by searching. So there is uninformed search strategies here. So then you can read this part, right? Okay. So please have a look this part, and after that I will come back, and again explain the topic. Actually, lecture 3, 4, and 5 taken from this chapter, of the textbooks. Artificial intelligence, a modern approach. It's about the problem solving by searching. All right, so we open the slide. Okay, can you see the slide?
Yes, sir.
Yes, sir.
All right, so Yeah, we are going to continue, but before we proceed for the second part of search agent, so I'm going to explain again about the DFS and PFS. Yeah, for additional materials for the previous lecture. Okay, so depth for search, yeah, actually search down one branch, yeah, that is depth for search, and after that until the depth, yeah, until the, I mean, the deepest of the branch. So if goal is not found and that end is reached, and backtrack to immediate parent node, yeah, and again go down to the next branch. So this is the example, yeah, start A, yeah, this is for the starting point, yeah, A, and goal is K. So how DFS works, so we will see here, until reach K, then the process will be stopped. Yeah, so this one, yeah, check if the current node is goal, yeah, if goal is goal, the goal is K, yeah, the start is A. So check the branch, yeah, the first layer here. So if not, then expand the node, yeah, if possible, yeah, and after that A close, yeah, and then start with the new node here, yeah, BC, yeah, branch. So A is a road as a starting point, and then expand, yeah, with B and C and A close. Yeah, and now B and C are open right now. And the next step, yeah, since this is depth for search, and go to the depth one, yeah, I mean the branch of the B. Yeah, we finish this part, and then yeah, A and B close because of B, yeah, given the branch here, yeah, D and E, right, as a child, yeah, so then B as a parent. So proceed this one, and then A and B close, yeah, and then C still open, yeah. Previously B and C open, but since B given the branch, yeah, branches here D and E, so then B close. So then C, D, E are open, yes, because of C is still open. And then the next, yeah, we finish this one because of this is the depth for search. Right, so finish until the deepest, and then we proceed to the next. If it is not found, the goal, then we proceed to the next, yeah, the next branch. Right, so check if the current node is a goal, K, yeah, if not, then we change to the other branch. So H is not the goal, right? Yeah. So this is the next, and then if like this, then D given two branches, H and I. So A, B, D close, right? So then now open C, E, I, H, yeah, C, E, H, I, yeah, the same, right? And then after that, yeah, check if the current node is a goal, okay? So if not, then expand the node, yeah, but it is a dead end, yeah, this one. So because of this is the dead end, so then close, yeah, then H this started, yeah. Now then go to the second branch, yeah, of the second branch for D, because of H is dead end here, yeah, this is dead end, yeah, there is no other branch. So then go to the next branch I here, and H started. All right, so then I, yeah, check if this is the goal or not. If not, then dead end. Then we go to the next branch, to the B, yeah, because so we finish this branch here. All right, finish. Then go to the next, yeah, the next branch from B, from B, yeah, which is E here. And if not, then expand the node, and after that, DHI here, DHI closed, yeah, or discharge it because so this is finished at that end. Yeah, now then go to E here. And then E, different branches here, J and K. Right? Then check. Yeah, if not, if E is not the goal, yeah, then expand the node. Yeah. Then yeah, now the goal K is reached because of E given J and K. J is not the goal, and then discharge it. Yeah, here. And then go to the next branch of E, K. So K is actually the goal. So now the goal K is reached. Yeah, here. The reach. And after reach, then stop. Yeah, finish because of achieve the goal. Yeah, because of it's mentioned in the previous scenario. Yeah, in the scenario that the starting point is A and the goal is K. Then if we reach the goal, then stop the process. Yeah, that is the depth first search. Right. So finish until this part. Yeah, because of the goal is K. If the goal is N, for example, or O, then we need to proceed. Yeah, we need to go to the C. Right. After K, yeah, then K, J, K, E will be discharged. Yeah, discharged here. Discharged it. Then after that, go to the C. Yeah, C, then F, L, yeah, go to M. Yeah, discharge it again. Yeah, and then go to the G. Yeah, and yeah, if N is the goal, then stop, finish. Yeah. So if not, then proceed to O. Yeah, O is, if for example, if O is the goal, then finish, reach the goal. Yeah, yeah, like that. That is a depth first search. So we go to deepest node first. Yeah, after that, proceed to the next branch. And that is the depth first. Right. So yeah, another tracing, the working of the depth first search can also be shown using an open close list. Yeah. So I mentioned also in the previous lecture about open and closed list. Yeah. Open. Yeah. Also here I mentioned. Yeah. So in this condition, yeah. In the previous one here, yeah. Yeah. This one discharged. Yeah. And this is still open. Yeah. This is closed. Yeah. What's it? The dark green. Yeah, here. Close. This is let's say this one is black. Yeah, these are black. Then discharge. So the green one here close already. So then we go to the branches and then go to the next. C is still open. Yeah. All right. So open and close. Yeah. 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 So then we can represent the tracing of DFS by using an open and closed list. An open list, also called agenda, yeah, contains the unvisited neighbors. That is the open. Yeah. Open means unvisited neighbors actually, and those nodes which have been visited. Yeah, and then a closed list contains those nodes which have been visited. Yeah, so that is closed list. Closed list. Right. So then if been visited, then stop. Yeah, I mean change to the other branch. And then once all the neighbors of a node are visited that node and its neighbors are removed from the closed list. Yeah. If all the neighbors of the node are visited that node, then its neighbors are removed. Yeah. So discarded. Right. So this is the same yeah illustration or same example as before, but we represent this as an open and close. Right? Yeah, the same meaning. Right? So A yeah first, yeah, because starting point is A. Yeah, we start with A. Yeah, start A. Yeah, and goal is K. Right? So we use the open and close here. So A open, yeah, and close is nothing, yeah, still at the first layer. And then we have a B and C this is parent or root, and B and C is a child actually. So the branches of A, yeah, and BC, yeah, and then if because all given BC, then A close, yeah, A close, and again B given DE, yeah. So because of B given DE here, then B A then B close, yeah, and open DEC, yeah. So DEC open, AB close, yeah, and then we continue with D, yeah, here given H and I, yeah. So ABD close, ABD close, and HIEC, yeah, HIEC are open, yeah. Continue until finish, like that, yeah, until we reach the K. So then we stop. If we K reach the K, yeah, and then K and C, yeah, open, and then here, yeah, ABE close, yeah, because this one discharged it already, yeah, remove from the neighbors. So then only ABE close here. So this is open, yeah. So then reach the goal and stop, yeah, finish until this one. So this how to represent DFS by using open and close representation, yeah. So we can use this also, yeah, to represent DFS, yeah, or to trace the DFS, right? So DFS algorithm, yeah, from one element list consisting of the root node, yeah, that is the one, and then while list is not empty or the goal has been reached, and determine if the first element in the list is the goal node, yeah. So if the first element is the goal node, then return, then success, yeah. So if the first element is not the goal, yeah, then remove the first element, yeah, the first element, discard it, yeah, from the front of the list and add its children, yeah, yeah, if any, yeah, if not the dead end, yeah, and to the front of the list. And the third one, yeah, return failure, yeah, list also known as agenda is implemented as stack, yeah. So stack is restricted, yeah, list in which insertion and deletion takes place only at one end, yeah. So if that end, then remove, then go to the next branch. So these are the properties of the depth first search, yeah. To be clear here, completeness, optimality, time complexity, and space complexity. Because of each algorithm has the properties, or we can say performance measure, yeah, to see the performance of to observe the performance of the algorithms, yeah, like this one, depth first search. So in terms of completeness, DFS, yes, yeah. If depth is finite, yeah. So then if you can reach the depth, then yeah, finite, stop, then complete, right? So if not, then of course, then we'll still continue until reach the goal. Yeah, and optimality not guaranteed, yeah, for this algorithm, yeah, DFS, and for time complexity, yeah, it is exponential time because of using the P power m here, yeah, for the P is branching factor and m is depth of the tree, yeah. So you have done exercise before, yeah, find the branching factor and also the depth, yeah, the level, yeah, we can say the level also. So then, yeah, this is very important, yeah, this one. And then time complexity and space complexity, yeah, time complexity is, yeah, and then space complexity, yeah, of bm, yeah, b times n. This is linear because of just b times m, yeah. So branching factor times the depth of the tree, yeah, for space complexity. Right. So now, yeah, breadth first search. Search all first level. Yeah, DFS finished this one. So now we continue with DFS. Yeah, to clarify all the thing. Yeah. Yeah, to explain, yeah, more clear here. So in BFS algorithm, yeah, so search all first level uh, children first, yeah. So this is different with DFS. DFS we find the deepest branch, yeah, the first type, yeah, the first node first. But in BFS we will search all first level children first, yeah, or all first level branch first, yeah, all first level branch, yeah, here. Branches for the next to the road. Yeah, if goal is not found, search all the next level children or neighbors and so on here. So this is the road, yeah, or we can say the parent, yeah, and then search, yeah, to all the next level. So all the next level is B and C. So we'll search B and C. Yeah. So the search process stop when either the goal is found or the search space is exhausted. And that is BFS. So for example, this is the goal is D, then start from A. Yeah, then goal is D. So we find by using the BFS, yeah, here. So we check the algorithm. Yeah, so first A, yeah, A is a road node, yeah, as the road. Then check if the current node is the goal. Yeah, the goal is D. If not, then expand the node. Yeah, if possible. So then expand. Yeah, B. Yeah, and C. Yeah. So we finish the first level. Yeah, first level after A. Yeah, after the road is B and C because of the branches of A is actually only B and C. Yeah. So B and C, finish B is not the goal, then go to the C. Yeah, go to the next, the same level. Yeah, that is the difference between the BFS and DFS. Yeah, we can see for uh, DFS, yeah, DFS just go to the deepest. Yeah, go to deepest. Yeah, this is the flow of process for BFS. Yeah, BFS we go like this. Yeah, and then go to this part first. Yeah, and again go to this part, this back to this one, and then continue to the process. Yeah, so that is the different. Yeah, yeah, okay, it's a process. So go to the all the first level first. Yeah, after finish, then for the next level. Yeah, so then B, then C. Yeah, so C check. If not, then expand the node. Yeah, yeah, then B and C is not, yeah, in here is not the goal, right? Yeah, because the goal is D. Yeah, so then we have to check the next level, the branches here. And B, yeah, the branches of B. So here, A, B, and C close, right? Because of already B and C given, A given B and C as a branch, yeah, as branches of A, and D and E as branches of B. So close, yeah. D, yeah, from B, then yeah, back to B, then check, yeah, from here, C, and then again back to B, and then check the branch, yeah. Okay, so if not, then expand the node, yeah, if possible. And if it is found, then stop, yeah, because of D is the goal, right? So stop. Then we can see here by using the open and close representation. Yeah, so A, yeah, the first the road, yeah, or the first this one, the root or the parents. Yeah. So the parent node here. So A open, yeah, at the beginning, and then close nothing, yeah, and then A has two branches, B and C. So B and C open and A close, yeah, because given B and C as branches of A, and then now A close, and now from B, yeah, we have after B, then we have a C D E, C D E, because after this, then we go back to B, yeah, yeah, and then we have a D E, right? We have a D E here, so that's why the open branches, open nodes are C D E, and closed node, yeah, A B, yeah, A B closed, yeah, and then after that, yeah, after DE, we got the open, yeah, DE, FG, yeah, because we have to go to this one, and this one, yeah, the same level. We finish all horizontally, yeah. This is in breadth first search, yeah. So then DEFG open, yeah, ABC, yeah, A, B, C close, yeah. But we reach the goal because of D is the goal, and we reach this one. Yeah, so close complete, yeah, for this BFS. Yeah, and then breadth first algorithm. Yeah, first one, yeah, form one element list consisting of the root node. Yeah, is the first step, and then the second, while the list is not empty, yeah, or the goal has been reached, and then determine if the first element in the list is the goal node. Yeah, if the first element is the goal node, then return, then reach the goal. Yeah, success. If the first element is not the goal, and remove the first element from the front of the list and add its children. Yeah, the branch, add the branches. Yeah, this is the same meaning. Yeah, branches or children, we say, and if any, and to the back of the list, and return failure because of not reached yet. And the list, also called agenda, is implemented as a queue. Yeah, the list we call as agenda, yeah, for the next process. Yeah, and will be implemented as a queue. And queue is a restricted list in which insertion takes place from one end, yeah, called as the rear, and deletion takes place at the other end, called as the front. Yeah, and then there is a rear and front, yeah, for this agenda. Yeah, all right. And these are the performance measure or properties of BFS. Yeah, yeah. In terms of the completeness, yes, yeah. By this one, yeah, we can say the completeness, yes, yeah. Then we will reach the goal, yeah, by the BFS, yeah. And optimality, the same as the DFS, yeah, not guaranteed, not guaranteed if this algorithm is optimum, yeah. And then in terms of time complexity, using BD, yeah, this is of exponential, yeah. So P is branching factor, and D is depth of the least cost solution. Yeah, so this is exponential, B power D. Yeah, and then for the space complexity, we use performance measure of the same also, yeah, exponential, yeah, using the branching factor and depth. Yeah, so these are the properties or the performance measure of breadth first search algorithm. Yeah, and then depth and breadth first, yeah, we can see we can observe, yeah, based on the given explanation. So both depth and breadth first strategies blindly search the entire search space. Yeah. So these are the most important algorithm, yeah, for DFS and BFS, yeah, for search agents. And then search is actually not guided, yeah, especially by path cost, yeah. And even though these strategies are simple, yeah, to implement, but they are very inefficient. Yeah. As mentioned in the previous lecture, also these strategies are actually not efficient, yeah, or inefficient. And then DFS is more space efficient as compared to BFS. Yeah. Yeah. In terms of the comparison between DFS and BFS, we can say DFS more efficient or more space efficient. Yeah. And then BFS search has the advantage of the completeness. Yeah. This is one advantage of the BFS. Yeah. As we can see here. Yeah. BFS. Yeah, completeness, yes. Yeah, we can confirm that by using BFS, the goal will be reached. Yeah, but by using DFS, yeah, still the condition here, yeah, completeness, yeah, yeah, it can be reached, but if depth is finite, yeah, if infinite, then cannot be reached. Yeah, the goal, and that is the condition. So at least BFS has an advantage, yeah, if compared to DFS, yeah, in terms of the completeness, yeah, because of DFS, there is a condition, yeah, if will be completed if tab is finite, yeah, if tab is infinite, then will not be completed. That is so. We finish this for DFS and BFS, yeah, with the additional explanation, because these are among the most important algorithm, yeah, to understand, because these are the basic and the foundation or the fundamental of search engine, yeah, before we proceed to the next one. The next one is actually the development of these algorithms, yeah, these strategies, yeah, DFS and BFS. The others algorithm are mostly development of these two algorithms, yeah, depth and breadth first. Part 2, yeah, after we finish learn about DFS and BFS, then we proceed for the next. Yeah, that's why I need to again clarify about BFS and DFS, because of both algorithms are very important, yeah, as a foundation for the next algorithms. Yeah, for the next strategies. Yeah, like DLS, yeah, IDS, PDS, and UCS. Right. So in this search agent part 2, yeah, the student should be able, yeah, to describe, apply, compare characteristic of these uninformed searching strategies. Yeah, category uninformed. Yeah, depth limited search, yeah, iterative deepening search, and bidirectional search, and uniform cost search. Yeah, so DLS, IDS, PDS, and UCS. So actually, these materials, yeah, are taken from chapter 3, yeah, in these textbooks. Yeah, I hope you all, yeah, already downloaded this materials. So I mean these textbooks. Then if you want to study more, then you can read from the textbooks. Yeah, because in textbooks, yeah, sometimes they give some additional explanation. Yeah, and we cannot explain all the content, yeah, in the textbooks, yeah, in the lectures. Yeah, because of during the lecture we have a limited time. Yeah, right. So the first one is depth limited search. Yeah, and then as we know that BFS is complete and optimal, yeah, but has a big problem in space complexity. Yeah, space complexity. even though the optimum still not guaranteed, but we can reach. Yeah, it can be reached by BFS. Yeah, but it has a space complexity. Yeah, for breadth first search. Yeah, and yeah, we can say the completeness is yes. Yeah, for this one BFS. Yeah, was it the performance measure? And then DFS, yeah, it's not complete. Yeah, still because of there is a condition for DFS. Yeah, as I mentioned before in the previous slide. Yeah, if the depth is finite, yeah, so then we can reach the completeness or reach the goal. Yeah, but if the depth is infinite, then you cannot reach, yeah, the goal. Yeah, and still actually not really not optimal, but still was it not guaranteed? Yeah, yeah. Sometimes because of if DFS we can say DFS completed, then we can also reach the optimum. Yeah, for this strategy, but still not guaranteed. Yeah. So, however, it has a linear space complexity and could be faster than, yeah, linear space complexity and could be faster than DFS. Yeah, because of DFS, as you know, that DFS will go to the deepest branch first. Yeah, so the deepest branch first, and if the first line, for example, is the goal, then it will be faster, right? Yeah, instead of, yeah, because of the DFS is like this. Yeah, will straight to the deepest. Right? If compared to BFS, it will be like this, and again back. Yeah, here and again back here. Yeah, sorry, down down to the branch, the next one, and again back to bottom. So it will like a zigzag like this, right? Until reach. But if was it the DFS just through the deepest, then if there is if the goal is found, then finish. That's why we can say DFS in terms of the speed, yeah, can be faster than DFS. Yeah, but in terms of the completeness and optimum, yeah, that is still not guaranteed. Yeah. But in BFS, it can be completed and also optimum. That is the advantage and disadvantage of both strategies. So in DLS, yeah, depth limit search, yeah, actually the same as DFS with the depth limit. Yeah, that's why I again mentioned about DFS and BFS. Yeah, because of it will be the foundation for the next strategy. Yes, for the other strategies. Yeah. So DFS is actually DLS here. DLS depth limited search is actually DFS. Yeah, depth first search with depth limit L, which is L. Yeah. So nodes at level L have no successor. Yeah. So we can assume that one. Yeah, because of it is given as or assigned, yeah, appointed as a depth limit. Yeah, L. So if we know some knowledge about the problem, maybe we don't need to go to a full depth. Yeah, yeah. If we know some knowledge, so we don't need to go to full depth. So that's why just give the limit L, then use the DLS, yeah, depth limited search. So this is like this is, for example, the idea any city can be reached from another city in at most L. Yeah, L. This is was step with L less than 36. Yeah, for example. So this is a example of the city in Canada and US. As you can see. So any city can be reached from another city. Yeah. So for example, from Vancouver, we can go to Washington here. Yeah. Yeah. So from Vancouver, we can go to, let's say, Dallas here. Yeah. So can be reached in any city. Yeah. At most L. L is the depth limit here. So if we have some knowledge, yeah, about this, then we can mention about the limit, yeah, the depth limit. Yeah, that is the benefit of DFS. So if we know the limit, then we don't need to go to the other way, yeah, to full depth, yeah, in this case. Right? Yeah, like road, this one. I mean the road from one place to the other place. Yeah. If we have knowledge about those place, yeah, or place those areas, then we can just go to the limit. Yeah. I mean we put the limit of the depth. Yeah. No need to reach all, or no need to visit all the cities before we reach the destination. Yeah, because we have knowledge about the location or the area. Yeah, that is the thing, right? So with one example, yeah, or illustration about depth limit. So depth limit search, yeah, limited search, yeah, actually a variant of the depth first search, yeah, yeah, this is a DLS, this is a variant of, yeah, DFS, yeah. So it's search still a depth level or cutoff, yeah, L, yeah, and the nodes at L are actually leaf nodes, yeah, leaf nodes. And choosing an appropriate L may not be easy and could result in incompleteness. Yeah, that is the one. Yeah, and L, yeah, equal to 2, yeah, in the following tree. Yeah, for example, yeah, the nodes in gray color will not be explored, right? So if we say, okay, the depth limited search, yeah, L, yeah, the limit is 2 here. So then we just go to the depth until 2, yeah, up to, which is from here, start from here. Yeah, we don't need to continue to the other, yeah, or we don't need to explore the other node here. So we just explore here, and then the gray color node here will not be explored. Yeah. So that is the depth limited search, right? So we go as usual. Yeah, go to the deepest one, yeah, here, yeah, and then to here, and then, yeah, back, yeah, to the second one, and the deepest, yeah, deepest, yeah, and again, and deepest, yeah, yeah. So those are the deepest, yeah. So but then we don't need to continue to this one, yeah. If we continue from the beginning, then we have to go to the bottom, yeah, the deepest one. But since we put the limit, then we just put until the second one, 1, 2, for the deepest. That is the deep depth limited search, right? DLS. So put the limit, yeah. And then the next is iterative deepening. Yeah. So iterative deepening combines the benefit of BFS and DFS. Yeah, that's why. Yeah. So we have to know clear about BFS, because so iterative deepening also actually the combination of BFS and DFS. Yeah. For DLS is actually the variant of DFS. Yeah. Yeah, actually the development of DFS. And then iterative deepening is the combination of the benefit of BFS and DFS. So the idea is actually iteratively increase the search limit until the depth of the shallowest, yeah, the depth of the shallowest solution for D is reached here. Yeah, and then applies DLS with increasing limit. Yeah, applies DLS, but increase the limit. Yeah, and it tries all possible depth limits. Yeah, for first depth, for example, 0, and then the depth 1. Yeah, this is depth 0. Yeah, for the depth, then depth 1, and then depth 2, and so on. Yeah. So the algorithm will stop if a solution is found. If the goal is found, then the algorithm will stop. Right? Or if DLS returns a failure or no solution. So it is an iterative process, and the depth of search depends Yeah, depends on at the each iteration. Yeah. So it is the preferred search method when there is the large search space. So then if it is large search space, then we can use this one. Yeah, IDS. Yeah, iterative deepening search. Yeah. And the depth of the solution is not known. So this is the condition. Yeah, if the condition like this, yeah, large space and depth of the solution is not known, then we can go by using the IDS. Yeah, and let's see the example with the depth limit between 0 and 3. Yeah, 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 this one. Before we go, then we see combination of depth and breadth first. Yeah, breadth first, this one. Relatively expand, yeah, almost the same. And completeness of BFS and lesser memory usage of DFS. Yeah, this is the benefit, or because of IDS is actually combination of the benefit of BFS and DFS, right? So completeness of BFS, yeah, we use this one, and the less memory usage of DFS. Yeah. So these are the advantage of both algorithms, and we use this advantage to be combined, and we got this IDS algorithm. Yeah, sorry, IDS, yeah, iterative deepening search. So this is an example, yeah, here for limit between 0 and 3. Yeah. So a TLS, yeah, if limit, so depth limit, limited search with depth limit 0. Yeah. And then a TLS with depth limit 1. Yeah. So with 1, this is 0. Yeah. This is example of 0. Yeah. Only the root. Yeah. If TLS with depth limit 1, so the root and children. Yeah. Branch. Yeah. Yeah. Right. Yeah. This is the root and this is a branch. These are the branches. Yeah. And close. Yeah. Okay, close and remove this one. Yeah. Finish. This is finish, yeah, for limit 1. And if DFS with depth limit 2, yeah, means that DLS, yeah, DLS 2. So we have 2 here, yeah, until the second level of branches here. Yeah. So A, B, C, yeah, and then D, E, F, G. Yeah, A, B, C, yeah, A, B, D, E, P has 2 children here, D and E. Yeah. And then C has 2 leaf also, yeah, or children, yeah, F and G. So will be like this, yeah, to finish the depth for search. So go to the deepest one, yeah, here. Yeah, deepest, this one remove, yeah, because of this one, these are the dead end, yeah, and close, yeah, and go to the next branch here for C. C has 2 branches, yeah, or 2 children, yeah, or we can say 2 leaves also, yeah, and then C close, yeah. A and C close, yeah, and then FG, yeah, go to the F, and then next G, yeah. So we got this one, and G, and then all close, yeah. So finish. So yeah, this one already for the TFS 2, yeah, with depth limit 2. Now what happened with if with the depth limit 3? Yeah. All right, I think over there the time for sur prayer, right? In
Yes, sir.
Brunei time, yes.
Sir.
So yeah, I give you 15 minutes, yeah, or 15 or 20 minutes for prayer break, and we continue this one, right? All right, so we continue the lecture. Can you hear my voice?
Yes, sir.
All right. So iterative deepening. So IDS we continue. So now the DLS, yeah, with limit 3. All right. So with limit 3 we can see here. So we go to the deepest, yeah. So the first one, second one. So one, sorry, this is 0, 1, 2, 3. Yeah, this is the third one. Yeah, so because of limit 2 we have finished this one. So what happened with limit 3? So we go to the deepest until the third layer here, the third level. All right, so from A to B, yeah, at the beginning, A is the root, yeah, then it has two branches here, B and C, yeah, and B and C, yeah, and then from A actually to B and to D, yeah, because of this is the deepest, yeah. So D, and D has two branches, yeah, here for H and I. Okay, so until we reach H, yeah, and then go to the I here, I, and after I, yeah, we reach I, so then D, H, I, yeah, close, yeah, this one, I close, then go to the next branch, yeah, after, next to B, yeah, the second branch of B, yeah, E, yeah, in this case E has two branches, J and K, yeah, so then finish J, yeah, visited J, yeah, and go to the K, yeah, here, and visited K, yeah, so then after that we finish the first one and the second one, yeah, this is dead end, yeah, and then after finish the first and second, yeah, visited all these neighbors, and then go to the second branch of A, yeah, which is C here. All right, so then C, yeah, has two branches, yeah, F and G, yeah, F and G. Then we finish F first because this is the deepest, right? Finish F. F has L and M, yeah, branches, and M visited L and then visited M, yeah. So L and M here L visited already and M, yeah, and then yeah, this is if we want to continue until finish all, so then we finish all. But if M is L is the goal, then we stop until L. Yeah, depends on which one is the goal, right? So if we goal O, for example, then we go to finish until reach O, until reach the goal. And so these are the process of the iterative deepening, yeah, IDS, iterative deepening search, right? So we put the actually combination of depth and breadth first search, yeah, PFS and DFS, yeah. So just take the advantage of PFS, which is completeness, and take the advantage of DFS, which is less memory usage. Right, so we can see different, the similar illustration with a different way of explanation. Yeah, so here, yeah, or A, it has A has B and C branches, yeah, for children, and then this one, yeah, go to the D, yeah, and E, yeah, and this one. Right. So these are the different way of explanation. So maximum search depth 3 and the goal is O, for example. Yeah. The goal is O. So maximum depth will be only 3. Yeah. Because of we have to go to the tab, yeah, and to the branch, and again to the next branch, tab, branch, and again to the next one, yeah, until reach O. Yeah. So so many stages, yeah, for iterative deepening search, IDS. So many stages are expanded multiple times. For most problem, the offer rate of this multiple expansion is actually quite small. And preferred search method when so IDS is preferred search method when there is large search space and the depth of the solution is not known. Right, so that is iterative depth. Yeah, this is the condition, the same. All right, and the completeness we can see here. The completeness is yes, for the performance measure, for IDS, and time complexity, B power D for exponential, and then space complexity BD, P times D, linear, and optimality, yes. So with IDS we can reach the goal, with the completeness and with the optimum way, So this is the time complexity BD. B is branching factor, and D is depth, depth of the least cost solution. So that's why the optimum or optimality can be reached, in this strategy IDS. So iterative deepening combines the benefit, this one, and then it may seem costly and wasteful, Many nodes are expanded multiple times, and then this is not the serious matter actually. So as we can see, the most of the nodes on a tree are at the bottom level, So it doesn't add much extra cost, if the nodes on upper level are expanded many times. So the total number of the nodes generated, we can calculate or count, for node, in IDS here. Node in IDS, actually D, times B plus D minus 1 times B square or power 2 plus, and so on, plus 1 B power D here. This is for the formula of BD, B power D. And then for node of PFS, the formula is B plus B power 2 plus, and so on, and plus B power D plus B power D plus 1. This one. So in this example, we given P with 10 and D with 5, then we can calculate the node of IDS and the node of PFS. So the node of IDS, D, given this one, D is actually 5. And this is node of, we'll count one by one in order to make it clear. For node for IDS here, if P is 10 and D is 5, so D is 5, so 5 times 10, right? So this is the first one, and plus D minus 1, D is 5 minus 1. You just put D minus 1 times P is 10, sorry, 10 power 2. And then plus, so here, so continue 5D minus 2, because of this minus 1, now we go to minus 2 times 10 power 3, until reach D. So plus 5 minus 3, right, times 10 power 4, right? So this is 100, this is 10,000. So 10,000 times 2, 20. 20,000. And then plus, because this is 5 minus 3, so no 5 minus 4, or 1. So we finish until 1 only. We cannot continue because so if we 0, then the result will be 0. Will be 0 for this one. And so 5 minus 4, yeah, which is 1. And then times 10 power 5. Yeah, so the result is this, right? So you can count 5 times 10, 50, right? And 5 minus 1 times 10 power 2, which is 10 power 2 is actually 100, right? This is 100. This is 100. So 100 times 4, so 400. And then 5 minus 2, yeah, times 10 power 3, which is 1,000, yeah, 1,000. So 5 minus 2 is 3. 3 times 1,000 is 3,000. Yeah. And then 5 minus 3, yeah, which is 2, times 10 power 4. 10 power 4 is 10,000. Yeah, this is 10,000. So 10,000 times this one times 2, yeah, will be 20. Right? And then the last one, yeah, 5 minus 4, yeah, it's only 1. Yeah, this is 1. And 10 power 5 is 100,000. So 1 times 100,000, which is 100,000. So I can write down here and IDS. Yeah, the first one, 5 times is 50, and plus, yeah, this is 5. And 4 times 100 plus 3 times 1,000 plus 2 times 10,000 and plus, yeah, 5 minus 4, 1 times 100,000. Right? So the result is this. Yeah, we can directly calculate 100,000, 123,450. So this is the number of the nodes. Yeah, for if branching factor is 10 and the dip, yeah, the dip is 5. You can imagine here. So it's a big number, right? This is for IDS. Yeah, for node of PFS. Yeah, so we can count here PFS. Yeah, the formula is P plus P power 2 plus, yeah, and so on. Yeah, plus P power D plus P D plus 1. Yeah, plus P power D plus 1. So we can count this one. Yeah, P is 10. Yeah, just 10. Yeah, this one. And P power 2, yeah, is 10 power 2 is 100. And P power 3, yeah, for 3, 10 power 3 is 1,000. And P power 4, P power 4 is 10,000. Yeah, P power 5, yeah, until 5, which is 100,000. Yeah, and then now the last one is P, yeah, power T plus 1. Yeah, so P T plus 1 is 11. So the last one here is actually 10 power 11. Sorry, D power 6, not 11, yeah, because of what's that? 5 plus 1. Yeah, 5 plus 1. Right. Yeah, it's almost 1 million. Yeah, yeah, around. Okay, so the total will be 1, yeah, million, yeah, 111,100 node. Yeah, this is the node. Yeah, the number of the node. Yeah, for each. Right. So you can try to count, yeah, by yourself. If you have a calculator or using your computer, you can try to count this one. Yeah. Let me check. All right. So it has the linear space complexity, yeah, as DFS, yeah, with this one, with also the O, yeah, B times D, and it is complete, yeah, and then it is optimal, yeah, optimum, yeah, if step cost is constant, yeah, for all operation, if all operation have equal cost. And then this one for bidirectional search, yeah, bidirectional search, we can see that to search simultaneously, yeah, this one simultaneously search both forward, yeah, from initial state, yeah, and backward from the goal. Yeah, so it will stop when two searches meet in the middle. So that is a bidirectional search. Yeah. So this is the start, for example. This is the goal. Yeah. So the complexity of this search, yeah, is actually BD over 2. Yeah, divided by 2. So because of the forward search and backward search, yeah, each have to go only halfway. Yeah, that's why this is half of the depth. Yeah, and this is yeah, B the half D plus B half D is much less than BD actually. Yeah, and however there are several issues for bidirectional search. This one. So in bidirectional search issues, yeah, must be able to generate predecessor, yeah, to enable backward search. Yeah. So, but this one, yeah, in some problems can be very difficult, yeah, to generate the predecessor. And then for the predecessor, this one for to enable the backward search, and how to deal with the possible goal state. So ideally, the problem just one or a few goal states. Or maybe you can unify it with one dummy goal state, yeah, if a goal is not an implicit, yeah, or is not stated clear. And then there must be an efficient way to check whether its new node already been visited, yeah, from the other half of the search. Yeah. So we need to decide what kind of search is going to take place, and the space complexity, yeah, for each half, and the space complexity is OBD half, OB half D, or OB D over 2, yeah, divided by 2. And this algorithm is complete and optimal if both searches are BFS. Yeah. All right, and then the next one is the uniform cost search, or UCS. Yeah. in some problems, the cost of expanding from one node to its successor might be different. This is the uniform. And by use road finding, yeah, in the example of the Romania cities, yeah, the distance from Arad to its 3 neighboring cities are different. Yeah, if you remember in the previous lecture, yeah, given the example of the finding the road, yeah, from I mean in Romania cities, yeah, from Arad to Bucharest, right? And how to leverage this information. And BFS will find the shallowest path. Yeah, this is for least number of cities visited, but we want to get the cheapest or the shortest solution. Yeah, not shallowest one. Yeah, that is the thing. I mean, actually want to find the shortest solution, not only the shallowest. And then modify BFS with prioritize by cost, not by depth. Yeah, by cost, but not by depth. And UCS is actually expand the node with the smallest path cost. Yeah, uniform cost search. Yeah, so then these are the uniform cost search. Yeah, and then explore nodes in their increasing cost can be implemented using a priority queue. Yeah, and similar. This is similar to BFS. Yeah, but takes path cost into account. It's an improved version of BFS. Yeah, that's why this all strategies are actually improvement or development of the basic or the foundation of DFS and BFS. Yeah, even UCS also the improvement of the BFS. So this actual path cost. Yeah, and then BFS finds the shallowest goal state, but in UCS, yeah, modifies the BFS by expanding the lowest cost node first. Yeah, that is the difference between BFS and UCS. Yeah, and then path cost is measured by cost function and order in priority queue. Yeah, uniform cost is equal to BFS. Yeah, if all step costs are equal. Yeah, so then if the condition, if all steps costs are equal, then UCS equal to BFS. Yeah, if this condition, if all steps are equal. Yeah, even though this condition is very rare actually. All right. Yeah, these are the illustration of the UCS. Yeah, find the shortest path from S to G. Yeah, in the following graph. Yeah, this is S. Yeah, the start point, and this is G is the goal. So from this one, yeah, we can see each path has the cost. Yeah, this is the cost. 1, yeah, from S to A, 1, from A to G, 10, yeah, from S to B, 5, from B to G, 5, yeah, and then from S to C, 15, from C to G, 5. So then cost of the node, yeah, from the start node is stored in the node itself. Yeah, for example, cost B equal to 5. Yeah, here. So if S to 0, S because of S is starting point here, so start point, so it is a 0. So S to A here, so you can see here S to A 1, yeah, the cost, and S to B 5, the cost. So the stored on this destination or area, and S to C, yeah, is 15. Yeah, you can see here, right? And then, yeah, so for the another expansion here, yeah, S to A, then A to, yeah, here, yeah, say 11, yeah, S to check, yes, it's to G, this is G, the destination. So S to A to G, yeah, will be 11 here. Yeah, because the destination is G. And then S to B to G is 10 here, right? So this is G. This is G also. Yeah. So from this, we can say that the answer is which one from this one? SAG or SPG? Which one? According to the uniform cost search. Because we find the least cost, right? So which one the least
SPG.
one? SPG, yes, right. So this is the SPG is the least cost node. Yeah, so then we select this one. Right. So this is the path SPG. Yeah, because of this one we got the 10. Yeah, SPG 10. Yeah, so these are the process. Yeah, from S. Yeah, if you make like this, more easy. Yeah, easier. Yeah, like this, because this is the trees, but this actually, yeah, the road like this, right? So S, yeah, there is no close. Yeah, S still open. Then from S, there is A, B, C, right? Yeah, A with 1, B with 5, C with 5, C with 15. So S will close. This is the new open. Yeah, then from that, yeah, B, A, B, C, then there is a G, G10, and then G11, then C15. Yeah, because of 15 here. Yeah. So this one, yeah. So this is for, I was at 11, G11 from here. Yeah, but all are, approaching the goal actually, because of the goal is only G here. Right, so then we'll get the B5, G11, and then was it for the still open? Yeah, this is still open. C15, yeah, for S and A close. Yeah, so this one close, yeah, because of already 11. Yeah, and then we got this one. We close this one. So G10, yeah, for this one, and then G11, of course, yeah, and C15, yeah, from this one. Then still open here, yeah, SEP. But since we got the 11 and 10, then we finish. Yeah, we got the 10 as the least cost, yeah, for this route. Right, so this is the pseudocode for UCS. Yeah, so I think the time is, yeah, for self-independent, self-directed study. Oh, so then we'll continue after self-directed study. So we continue this one. This is the pseudocode for UCS, yeah, for uniform cost searching. Yeah, so open the start node with the cost 0. So because of in UCS actually we find the least cost node, right? Yeah, the least cost node. So this is one important thing that we need to consider when we develop this UCS strategy. Right, so then start node with cost 0. Yeah, so because at the beginning, yeah, this is the starting point, and the cost will be 0. And closed empty, we have open and closed. And then while open is not empty, yeah, then do, right? Then remove the first state from open, yeah, and we call it X. And then put X is in closed, yeah, as we can see here, yeah. So this S, yeah, then at the beginning S will be, yeah, S open, then the other one closed, and then put the second one as an X, yeah, here, and put X in close. Then we have to find the what's it, the branch, yeah, the next step, yeah. Yeah, so if X is a goal, then return path from start, yeah, to X, and then generate all successor, yeah, for X, and for each successor of X that is not in clause, then do this one, yeah, if and if else. So if successor is already open, already visited with worst path cost, update open, yeah, open info to reflect the new path and cost, and else add successor to open according to the path cost. Yeah, so that is the condition. Yeah, if it is not in close, yeah, so they need to expand the new branch, yeah, the new what's it, the path, yeah, the new path, this one, and then after that in the new path, then we see the cost, yeah, update as an open, then reflect the new path on and cost. So that is the code, yeah. Actually, yeah, because of we can represent this UCS by open and close representation, yeah, as the other algorithms or strategies. Yeah, we can use open and close. So this when we write the shadow code, then it will be more appropriate if we use open and closed. And then if BFS versus UCS example here. So go from Chicago here, for example, to Sault Ste. Marie. Yeah, here. Yeah, so from this is start. This is what's it, the destination. So using BFS, we would find Chicago. Yeah, and Duluth here, and then Salt. Yeah, this one using what's it, the BFS. If using UCS, we would find Chicago, Pittsburgh, yeah, because so we find the least cost, right? So Pittsburgh, yeah, and then Toronto, yeah, and then go to St. Mary here. So this one, if we use UCS, yeah, if you use BFS, yeah, BFS, we do not consider the least cost, yeah, or the cost. You just find the bread fund, yeah, and after that, find the next branch, yeah, for them. So the destination is this one, yeah, St. Mary here. So which is actually the shortest spot in terms of the, yeah, we can see here, yeah, if we calculate here, yeah, from Chicago, yeah, Chicago go to Pittsburgh, yeah, this is Duluth, and then this one St. Mary, right? So then 110,157, right? And then for another one, yeah, Pittsburgh, and then Toronto, and then reach the St. Mary. Right? So this is 81, Pittsburgh, Chicago to Pittsburgh, and then Pittsburgh to Toronto, here 80, and then this is 90. So we got this one, yeah, 114 BFS. Because of BFS actually it doesn't consider this one. I mean the least cost, yeah. So plus 157, right, which is 2, yeah, 6, 7, right? Right, and how about the UCS? How about UCS? 81, right, plus 80, right, plus 90. So we get 90, 170, yeah, and or 170 and ET1, yeah, 251, right? So which is this one the shortest path actually because of the least cost, yeah, and most probably the distance also. If we say this one the distance, then will be the shortest part, right? So you see, as even though we follow two cities, yeah, before reach St. Mary, Pittsburgh and Toronto first, but this one using Duluth, yeah, for St. Mary, only one city, but still the distance or the cost higher than the other one, right? So means that UCS more, yeah, in this case, efficient, right? So because we got the shortest path, yeah, with the least cost or the shortest distance, we can say. So example, another example from start from node A, yeah, and then call node G, yeah. So this is start, and this is goal. Yeah, so from this we can find, yeah, the road, yeah, or the path, yeah. So the priority queue, yeah, this is open from the start, and the counterpart is, yeah, 0, yeah, or still blank, yeah. So then A with 0, yeah, this to expand, and then another one we go for D3, yeah, this is 3, yeah, because A 0 is a start point, yeah, and B, yeah, with 5, yeah, this one, and next D, yeah, to expand this one D, yeah, then this one A is closed, yeah, this one closed because already given two branches here, yeah, D and B. So we go to D, yeah, the first one. We have two branches, yeah, E2, yeah, sorry, D is one, yeah, with the, because of E, until A is 5, yeah, 2 plus 3, yeah, so E5, yeah, if from D, yes, but if this one, 2A, yeah, so another one F actually also 5, yeah, because of this one to A, yeah, the distance from F to A is 5, and then, yeah, B is still 5, B is still open here, and then now, yeah, B here, and then expand from B, yeah, from B we go to B, yeah, this one, then we got the, yeah, E, yeah, with 5 is 1, yeah, because we go to actually from A, yeah, and F, yeah, also 5, yeah, here, yeah, and then C with 6, another one. We find the what's that, the nearest one, yeah, the closest. Even though we can go to from B to E through this way, but because of we have the nearest part, so then we go from E to A, yeah, through the D. Right, so ADB, then until finish, yeah, the goal is G, yeah, with G8, so we can see here 3, 2, 5, yeah, GH, and found, yeah, G found, and then the others close, yeah, A, yeah, from A, D, B, yeah, E, and F, and C, yeah, close, and goal found here, G. Right, so this is for UCS. So you can explore more this information or this knowledge from this one also, this link. Yeah. And then breadth first search can be viewed as special case of UCS, yeah, actually. So BFS actually can be viewed as special case of UCS. So if the cost of going from one node to the successor nodes on the next level are always the same, then uniform cost search is equivalent, yeah, to BFS. Yeah, if all the next level, yeah, I mean the successor nodes on the next level are always the same, yeah, it's the cost. So UCS we can say equivalent to, yeah, BFS. Right, so in other words, BFS is simply UCS, where the cost function, Gn equal to depth n. So always the same, the cost of the from one node to the successor node, until the depth. So in this case, UCS completeness, yes, if cost of every step is more than equal some small positive constant E for the element of this. And then optimality, yes, because it's select least cost for unexpanded node. And how about the time? So it depends on the process and the cost as well. So you can see here, suppose C star is the cost of the optimal solution, and we estimate how deep the optimal solution could be to roughly this one, divided by E is lower bound on the cost element, we say. And time complexity depends on this one, asterisk of node. This one is and then this is the crossbar of nodes with Gn less than equal the cost of optimal solution. So for the worst case, can be estimated to be C asterisk this one or star divided by E for the lower bound on the cost, and which can be greater than P power D for in the worst case. And then the similarity, this one, number of nodes, this case, and with G, number of nodes and number of nodes with Gn, less than equal to cost of optimal solution, this one. So it's an example using a map, so from Las Vegas, goal. You can see the Las Vegas, Las Vegas here, for example, and then the start, and then the goal is Calgary, and you can try this one, to find, to apply BFS, TFS, and UCS, for if you want to, make it better understanding, you can make it like a tree, from the Las Vegas, what the direction, for example, to Salt Lake City or LA, and then from the LA we have how many branches, for each, right? Okay, so these are the example using a map, for BFS, so from Las Vegas here, so you can see, the road, Las Vegas, Los Angeles, Salt Lake, the Salt Lake City. So because from Las Vegas, there is two branches, Los Angeles, LA, and Salt Lake City. And then from Los Angeles, there is El Paso here, and Phoenix and San Francisco, from LA. And then from Salt Lake City, there is a Denver, and Portland, here Portland, and and Denver, Portland, and Helena, Helena, Portland, right? So then from the El Paso, there is a Dallas here and Santa Fe, here. So the branch from each, and then from Denver, the branch is through the Omaha and Kansas City, and from Helena reach the destination. So this is the way and the city visited, using BFS. So you can see how many cities visited, until reach the Calgary. If we compare with DFS, you can see here DFS, with the depth first search, from Las Vegas. So we go to Los Angeles, Los Angeles, and Los Angeles, El Paso, because of the deepest until reach the destination. That's why sometimes deepest DFS more efficient, or reach the complexity. I mean, the completeness. The completeness is yes if the deepest is finite. That is the thing. So if infinite, then we cannot complete. Right. So El Paso, Dallas. This is the example of using DFS. So from Las Vegas, to Los Angeles, because to find the deepest, then El Paso, and Dallas, Houston, New Orleans, then there is Atlanta here, and until Calgary, and then for the UCS, we find different approach, because so in UCS we look for the least cost, so consider the least cost. So these are the almost similar with BFS, which you see here, but it takes the advantage of the BFS and advantage of the DFS. This is the UCS, right? So Los Angeles, so we follow this from Las Vegas to Los Angeles, and then Salt Lake, almost the same, like if we compare to this one, this similar like this, right? Like BFS, So that's why if the distance is the same, then we can say UCS is equal to BFS, So if the distance is the same, then UCS equal to BFS, this one, right? If the distance is not the same, then a little bit different, but similar, right? So these are the illustration, and then the summary, the algorithm. So the criterion, BFS, and then UCS, DFS, TLS, and IDS. You can see the completeness, For BFS, yes, we can say, and UCS also yes, because of UCS and BFS is similar. If the distance for each successor, the next successor are the same, so then we can say UCS is same or equal to breadth force, BFS, and then depth force here, depth force no, means that it can be complete if the deepest node, the deepest node is finite, right? So that is the condition. And depth limited, also similar to DFS with the limited level. We put the limit, and IDS, iterative deepening. So then we can say this one also complete, iterative deepening. Yes. So these are how to calculate time, and space, So different formula for each, and then for branching, this one, then depth, and P is branching. So then L is a limit, so for each. Then the space, this is the formula for each. And then the optimum, we can say BFS is yes, UCS also yes, and this one for DFS no, TLS no, and iterative yes. So as long as it is completed, then we can say optimum, but actually depends on the calculation, the road also. If we compare all, so then we can see which one more efficient. All right, so finish for this second part of search agent, right? So you have done the exercise, for the breadth first and DFS, and then you can do some exercise also for this one, check the road and so on. Then now we try BFS and DFS with Google Colab. So we see, because actually we can provide, can do the programming by using the tools. So then we can find very fast, of course, instead of the manual calculation as mentioned in this theoretical part. So we can perform this the searching algorithm, searching strategy, also using the tools. So the do you have a Google account, right? All of you?
Yes, sir.
Yes, sir.
Yes, sir.
So
Sir.
in order to sign in to Google Colab, we need an account of Google, Google account, Gmail, and then after that you can, at the beginning we can go for, I will check the Google Colab. You just type Google Colab, on or said the browser, on the Google engine, and then you will get the basically Google Colab using the Python, Python platform here. So I will show you. So you can try right now, open Google Colab. You can browse the Google Colab. If you have experience, then good, so not so difficult. But I want to show you at the beginning here. This one. Can you see the slide here? The browser, my browser here.
Yes, sir.
Yes, sir.
Okay, so this is because I'm already signed in, so you can see this one. I did some experiment here. So if for example, if you want to create the new one, when it appear like this, then you go to the new notebook here. You can see here, new notebook, the cursor I shown you here, new notebook, and you will go to new notebook. All right, this one, and then you just enter the code here, the code Python base here. Can you try on your computer to open first? Open the Google Colab, and after that sign in using your Gmail. So first open, then make sure that you reach this in your computer appear this display, like this. This is for the new, you can also, this one, there is a new notebook, and if you want to add the code, you just add here, code, and the next one. Can you open? Just take your time, you to explore the Google Colab, because it is actually very useful for the Python base, especially if we know for very fast for learning, for the first learner, this one. And then if you have experiment, you can perform this one here by typing the code. I will show you, I will give you the code, then you will try for DFS first, and after that BFS, then try to execute. Right, so I will show you the practical one. So this is the DFS. This is the DFS, for and then this the code. Yeah, you need to type on your Google Colab. Yeah, here. Yeah, and then after all this one running, yeah, this one executed, then you will get this one, the output. Yeah. So actually, this is the diagram of this. Yeah, the for tree structure. Yeah, in the figure below here. Yeah, with the A as a parent. Yeah, and there is a three branches. Yeah, three branches here. Yeah. B, C, D, right? So branching factor is 3, and then the deepest, yeah, D is only 2. Yeah, B and PE, yeah, these are 2. And then from this one, yeah, traverse and output the path from all leaf nodes, yeah, to the root node. Yeah, to the root node is all leaf, yeah, E, F, G, H to the root node. Root node is A, right? So how to implement, you write down this Python code to the Google Colab, and after that try to run. So how to distribute? You see this one like this. Can you see the code here?
Yes, sir.
Yeah. So if you open the Google Colab, yeah, yeah. So you need to write down this part. Yeah, import pandas. Yeah, is a library here using pandas, and then after that the code here, yeah, for to get the to mention about the child father, yeah, dictionary. Yeah, it start, and then starting from the leaf node and traverse continuously to the root node to get the path from all leaf nodes to the root node. Yeah. So for example, this is the child, yeah, child father dictionary. Yeah. C, yeah, here. C, yeah. So C, the branch, yeah, is actually D and B. So you can see C, sorry, the was it the branches, yeah, the same level, this one branches, and then for D, yeah, D here, yeah, yeah, A, B, this one, D, A, yeah, D, C, A, C, yeah, D, B, D, B, yeah, and then D for A, and also B for A, yeah, so D actually child for A, yeah, A is parent, yeah, and then B here is child of A also, yeah, yeah, and C with the B is equal as children, yeah, BCD, children of A, the parents, and then return all path, yeah, with the CB, yeah, the children of A, yeah, and then CD, yeah, CD, CB, CD, the children of A, yeah. Right, so you just type this code and then try. If finish this one, then let me know, because so you need to continue with this part. So I will check. I think this one okay. Can you see this? You can see all from here. Okay. I will make it this one. I will make it down. Okay, so then you can see all. Okay. All right. Yeah, this is all. You can see this all. All right. So try to create the new code notebook on your Google Colab, and after that we see the execution. After this, I will show the how to execute. Yeah, please try. So because this one. So please check again, yeah, if you have done this one, the first part. Yeah, first part. Yeah, the implementation of TFS. Yeah. So in Google Colab, the first part, this one. Because of the previous one using Word, then maybe it will be confusing, yeah, since there is many disturbance here, line and so on. So this one is clear. And then the second part, yeah. All right. Yeah, this one. Or I make it full, maybe better. Okay. But still. This is first part. This is second part. Yeah. Did you finish this part? The first part from import pandas, yeah. SPD here for a library until this one. Yes,
Yes.
Amir. Okay,
Yes,
this
sir.
part finished, yeah. All right, so now you go to the second part here. Second part, you just type, yeah, even on the same notebook also no problem, yeah. I mean the same was that the new code, yeah, the same code, yeah, the same one. Then not necessary that you need to again open the new code, yeah, add new code. Why I give you like this, because of to make you was familiar with this application, yeah, with this platform using Python and Colab. After that, then because of you can also do copy paste this one, but for the I mean the first lab here, yeah, I think I want to train you to be familiar as well, and then after that, then you can explore many things from this, yeah, because so if you write one by one, then it will be more, you will get more understanding, yeah? Instead of you just copy paste all this and then after that copy this all code and after that paste on the platform, yeah. So after you done this, yeah, write in all this code, then after that I will show you how to execute the code, yeah, on Google Colab. Or some of you have been familiar with this Colab, Google Colab. Do you use before Google Colab? Samir, Martin, did you use this application before? Maybe.
Google Colab, yes.
Oh,
Yes,
then,
sir.
Yes,
oh,
sir.
that's, yeah, great. So means that you are familiar with this application. So then, yeah, not difficult to perform. Yeah, because of for teaching purpose, yeah, it is a convenience using this Colab, yeah, instead of like what's it, Prolog, yeah, because of in intelligent system, yeah, we have a Prolog also, but Prolog is actually this is the old version, yeah, the a long time ago we used the Prolog, so some of this change. I mean, people change with the latest platform, TensorFlow, this one, yeah, Anaconda, yeah, Python. So it is better to use the current platform, yeah, instead of use the old platform, yeah, the old one. Prolog is fine, yeah, before, because I learned Prolog a long time ago, maybe more than 15 years ago, yeah. So that's why, yeah. Then it's been a long time, and yeah, yes, it is a basic logic programming, yeah. But then maybe for today, yeah, it is a yeah, because of there's many convenience and yeah, easy to learn, yeah, application, yeah, instead of using the old version of the logic programming. So then if you finish, then try to execute, yeah, what will happen, yeah, this from this, and the output should be like this, yeah. Yeah, because of this is the output of depth, yeah. So until, yeah, from A, yeah, because of E is the if you see this one, yeah, E is the child of B, yeah, B child of A, right? So you can see here the output, yeah, actually it represent the diagram, this diagram, yeah. So E, yeah, this E is one, as I showed you here, child of B and B child of A. Yeah, so A is the parent, yeah, or the root of these three diagram. So we can see here the first one, and then the second one, GDA. So you see here, yeah, GDA, yeah, is the same, or we can say FCA, FD, FPA, yeah, CCA, GDA, HDA. Yeah, so we have how many depth? 1, 2, 3, 4, 5, 6. right? 1, 2, 3, 4, 5, 6. Yeah, we have six steps, yeah, from the deepest node, yeah, to the root, yeah, to the root. The root is A. So all have a relationship with A, yeah, because of A is the root of these all branches. So EBA here, EBA, FBA, FCA, GCA, GDA, and HDA. So at the beginning, A has 3 branches here. Yeah, B, C, D. Yeah, the children, and then B has E and F. C has F and G. Yeah. Then D has G and H. So you can see here. So then all E, F, G, H, actually the dead end, yeah, the dead end of this trees diagram then has a relationship. This all have a relationship with A, yeah, as the root. So then we have 3 branches and D2, yeah, depth. So this yeah, B we have a 3, and for depth, yeah, we have 2. Yeah, as the question on the previous lecture, right? The exercise. Yeah. The branching and also the depth. All right, so the result should be like this. Yeah, the output, yeah, because so we want to traverse this, yeah, these trees diagram and output the paths, yeah, from all leaf nodes, yeah, to the road. Yeah, all leaf nodes is actually these are leaves, yeah, right? Because of the road is only A in this case, right? So A has 3 branches, yeah, and then each branches has a 1 and 2 share, yeah. I mean 1 share and actually 2, but 1 share, this one. So then, as I mentioned previously, then supposed to be E, yeah, as a relation with the B and A, yeah, I mean the path, yeah, the path, yeah, FBA. So EBA, FBA, FCA, GCA, GDA, and HDA. So we try to see the result. This is the final output actually.
Yes.
So this is actually the same thing, yeah, from the PDF, yeah. So then this is the code, yeah, from Notepad, and was it the child father dictionary, this one, yeah. And then after that, yeah, this is the result, that output that we mentioned, yeah, FBA, FCA, yeah. So all will have relationship with A, yeah, because so A is the father for this, I mean the root, yeah, in this case. So then, yeah, there is a ABA, FCA, GDA, GCA, EBA, and HDA. So we can take one by one actually, yeah, for this code, yeah, from this one. We just copy paste this one, yeah, yeah, until this, yeah. Sorry, and DF this one until this one. Yeah, and after that we type DF, yeah, to get this one, yeah, from the data frame. Yeah, so the relation, yeah, the father A, yeah, and child B, and AC, AD, yeah, A has 3 children actually, yeah, BCD, and then B has 2 also, EF, and C, FG, yeah, has 2 also, and D, GH. So these are the relationship for each, the relation of father and child. So when you run this one, then it will appear this. right? Because this is actually the execution. Yeah. So we got this one. Yeah. And then go to the next here. Yeah. If you copy, check this one, the father set. Yeah. And then child set, yeah, for father and child. Then you need to import the Panda first here. Yeah. Because of the PD data frame, yeah, we have to run the first one. So then you will get this one. So you can try one by one actually. Set, yeah, father set, yeah, with the set father. Then this is the result, yeah, and this is for another one, yeah, and the leaf node set, yeah. What is the result of leaf node set if you run by using the collab here, yeah. Yeah, and so on, yeah, until finish. Yeah, you can check one by one what is the result from each code here. Yeah, so then these are the final result. Yeah, the final one. All right. Yeah, breadth first search. Yeah, for the path. Yeah, if we want to perform the code, yeah, by using collapse. Yeah, so then you can do like this. Yeah, you just use this one. Yeah, yeah, the graph. Yeah, for 5. Yeah, it has 3 and 7. Yeah, and then 3, it has 2 and 4. Yeah, and then after that, go to 7. Yeah, because of a breadth is actually, yeah, it's actually then we need to go to the again to the next one. So after that, 2, yeah, 2 n, yeah, actually 2, because of 2 dead end. Yeah, and then for 4 it has 8. Yeah, and 8 dead end also. Yeah. So it's with this sequence, so we draw this one, yeah, and put the code on the Google Colabs, yeah, then we will see the result. So this you can check this one, yeah, try to provide to write this code, yeah, and then after that try to check the result. Yeah, to get this the output actually. The output will be the following, yeah, for BFS, yeah. 5, 3, yeah, because of the road, yeah, 5, 3, yeah, 2, yeah. Sorry, 5, 3, we have to go to 7 first. 5, 3, 7, and after that go to 2, yeah, right? 2, and then after 2, 4, 4, and then 8. Yeah, so this is the process of, because of that first, so we have to go to 5. Yeah, first start at 5, 5, 3, yeah, 3, 7, 7, 2, 2, 4, 4, 8. Yeah, so then we get the result. This one, yeah. The sequence will be 5, 3, 7, 2, 4, 8. The output. Okay, so then you can try this one. And then after this, before finish, I will explain about the assignment 1, yeah, for individual assignment. Yeah, we have 3 weeks, yeah, to finish assignment 1. I will explain, yeah, after this. So check this algorithm first. I mean this code first. Yeah, then we'll see. Before we close the session, I will explain about assignment 1. Copy on the your Colab. and try to run. Then the
Yes,
result.
sir.
Yes, sir.
Okay, good. So did you get the result like this?
Yes, sir.
Okay,
Yes.
great. Yeah, good. So then is the result for BFS. Yeah, so by using the Colab is actually more convenience. Yeah, so you could just, I mean, because of the basic of the Colab is the platform is Python. So with this Colab, so then we can explore many things related to AI, artificial intelligence. Yeah. Even neural networks, GA, yeah, and then related to machine learning. Yeah. So later we will study also some part of this application, yeah, by using Colab, yeah, some example and maybe the problem solving, yeah, by using this application, this code. So I will share with you for BFS. So can you see?
Yes, sir.
Yes. So then it's exactly the same, yeah, as written on the lab sheet, yeah, on the paper. So then when we run this one, yeah, so we got this one, and then we can also run each of these one by one. For example, grab this one, yeah, and just type and put the here, yeah, and then we see write the graph, and we will execute and we'll get this result. Yeah, this is the graph actually for the case that I showed you. Yeah, and then this one, the visited nodes. Yeah, so the list of visited nodes, and you can just copy paste this part. Yeah, yeah, until, for example, until Q, yeah, append the neighbor, then you run this one. Yeah, with the BFS visited, yeah, graph, and you will get the final one, this one. Yeah, the result of the BFS.